Problem number 2050, parallel courses 3. You are given an integer n, which indicates that there are n courses labeled from 1 to n. You are also given a 2D integer array relations, where relations j equals previous course and next course. Denotes that previous course has to be completed before course next course. So it's a prerequisite relationship. And furthermore, you are given a zero index integer array time, where time I denotes how many months it takes to complete the I+1's course. So the course is labeled from 1 to n. Okay. So you must find the minimum number of months needed to complete all the course following the rules. You may start taking a course at any time if the prerequisites are met. Any number of courses can be taken at the same time. Return the minimum number of months needed to complete all the courses. The test cases are generated such that it is possible to complete every course. Okay, so there will not be cycles, and it will be a directed cyclic graph. Okay. Okay, I want to clarify that. So the course is labeled from 1 to n. There's no 0. So the relation j, the array in the relation j, it will not appear 0, right? So it will only have 1 to n for prerequisite and next course. And what about, okay, time I means time. Okay. Oh, relation length can be 0. Okay, so there is like a prerequisite relationship, so I would like to try a topology sort. Yeah, so the first thing I would do is to build a graph that, and also the degree count for each courses. Yeah, and then we have the time, so it's like yeah, when we do topology sort, we should take the time into consideration. Yeah, like, okay, so first build the graph. Yeah, and for topology sort, I would like to use BFS. Okay, so yeah, okay, so for like if we want to take, take example 1 for example. Yeah, if we want to take course number 3, we need 3 months. Yeah, we need 3 months, and then to finish the prerequisite thing, and then we can take course number 3, and then we add it up. Yeah, taking course number 3 is we need 5 months, so it's 3 plus 5, it's 8. So totally we need 8 months. And then that's the we can start for the courses. Like topology sort, we can start the courses from the in degree that is 0, and then we take its maximum. Like, okay, so one course number 1, 2, 3 has in degree 0, so we will take them first, and then for course number 5, we will maximize its prerequisites, but okay, so its time will be dependent on to have course 4, we need 3 months, and then because it's its prerequisites only have 3, so course number 3, so it will have 3 months to finish its prerequisite, and we can have course number 4. And then for course number 5, it will look at maybe it's like dynamic programming thing. So when we are at course I, it is the months that we need to take for the neighbors, like the prerequisites courses that we need to take. And the maximum, we need to calculate the maximum, and then plus our time itself. Okay, we can first build the graphs, and then and also the in degree thing, calculate the in degree. So graph will be a default dictionary, and it will be default to list, and we'll have an in degree. We'll have 0 as default, and then we will have n plus 1. Okay, so for pre and course and next course, and then have next like this in relations. Graph proof to next, and in degree for next 1 plus 1. Okay, and then we use like if the relation length is R, then we'll use OR, time complexity. And the phase complexity for graph is n plus r, and then in degree is n, on. Okay. Then we will start our topology sort. But before starting, we need we need the minimum time to complete all the courses. I will say time needed time needed to complete course I. So it will be I think we will have time at first. I want 0. We'll have dummy node so that the index will be will be aligned with the course number of course in the graph. So it will like this. And we will start from the courses that don't have prerequisite course. So for IN degree, enumerate in degree dot degree is 0. And while Q has value, course equals Q pop left. Okay, so for this course, starting from the course that has 0 degrees, the time they need to finish the course it's the time itself. So and then for its neighbor, for next course in graph course time needed for next course will be it will be the time needed think it will be better to have 0 first. So it will be n plus 1. And then we will compare its prerequisite for we'll take the maximum. So max time needed course with itself and then in degree will be calculate. So in degree next courses will minus 1, and if time if its in degree reaches 0, then we will add its time needed. We will add itself. Will plus time next course. The time itself it needs to take, and then append to the key. Or we can do it here. We can do it at the course when the course pop out, so that the in degree the courses that has in degree 0 we can be deal with. So we can do it like time needed course plus time course minus 1. Because every course will be added to the queue only once. So we can have let's see, relations can be 0, so there can be n can be only 1. So let's see if we haven't finished, so we will return we will have time needed to finish course. So we will have the maximum time needed as the answer. Okay, so yeah, edge case will be like okay, n equals 1. If n is 1, then we will, relations will be an empty array, so we don't have a graph. We will have an empty graph. That means we will have like this, and then for in degree we will have, it will have a length with 2. So it will be like this, and relation, we will not enter, so it's like this. And so topology sort time needed will be this as well, and Q will have 0. Oh, sorry, we will have 1. Oh, we will have 0 and 1, but we don't have 0, so we will if I not equal to 0 and we will have 1, and while Q is having an element, so cores will pop, 1 will be popped, and time needed for cores, okay, so time will be time, okay, time is like 10. Time needed cores will plus, so 0 will plus time cores minus 1 is 1 minus 1 is 0, so 10. So time needed will be 10. And for next cores in graph cores, okay, unfortunately it's an empty, so we will not run. Okay, and then since Q is already empty, we will not, so maximum will be 10. Correct. Then we will have, we'll run the example 2. So n is 5, and then we'll write it here, like graph will be 1 with 5, and then in degree, okay, we'll have n is 5, so we'll have 6 elements. Okay, so for this we'll add 1 because next is 5. Okay, and then 2, 5. So 2, 5. 5 will add 1 again. 3, 5. 5 will add 1 more. 3, 4. So 10, 4, and then 4 will be 1. 4, 5. Okay. 4, 5, and then 5 will add 1. Okay, and then move on to the topology storage. We will have 6 elements as well, and okay, and for the integrity that is 0. Okay, so it will be, we cannot be equal to 0, so 1, 2, 3. Yes. Okay, so course 1 will be popped. Course 1 popped. and then time needed for course 1, this will be time 0, so it's 1. And for the next course in graph 1, in the neighbors of graph 1, it's 5. Okay, so time needed for course 5, it will be time need is 0 before 0, and time needed course it's 1. Course is 1, time need is 1, so it's 1. And in degree, it will minus, it's left 3. Okay. Then it's in degree is 5 is in the in degree of 5, course 5 is not 0, so we'll not enter this condition. And then we will move on to Q is still having elements, so we'll pop 2. So time needed for course number 2 here, it's plus time 1. Time at index 1 is 2. And then for the graph of course 2, it's 5 for its neighbor next course. So time needed for 5 is time needed 1. Next 5 it's had 1. Time needed 2, so it will have 2 maximum. And minus 1 for its in degree is still 2. And its in degree is not 0, so we will pass this condition and move on to the next course. Q is still having elements, and we will now pop 3. Okay, so for time needed course number 3, here, this one is time plus time at index 2, so it's 3. And then for the next course in graph 3, it has 5. 5 and 4. It has 2 neighbors. So time needed for course number 5 will be its origin time 2, and time needed at course 3. So 3, it's 3 now. So it's 3. Updated to 3. And then in degree of course number 5 will minus 1. It's 1 now. And its in degree is not 0, so we'll pass. Okay. And for graph, we still have neighbors of graph 3, course number 3, so it's 4. So next course of 4, its maximum will be, its time needed will be itself is 0 by default, and time needed for course 3, so it's 3. Updated to 3, and its in degree will minus 1 and it's 0, so it will enter this condition and append it to the queue. So we'll have 4 now. Okay, and so the neighbors of course number 3 has finished, and now we have course number 4 popped out. Okay, so course 4, the time needed for course 4 is 3 plus 4. 4 in time. 4 minus 3, index 3. It's 4. Okay, so it will be 7. And for the graph, for the neighbors in graph 4, it's 5. So time needed for course 5 is maximum of its original time needed is 3 now, and time needed for course 4. Okay, so it's maximum, and we will update to 7. And then in degree minus 0, minus 1, so it will become 0. So we will append 5 to the queue, and then we will pop out this course. So time needed for course 5 is, will add up the time in the time array. So it will be added at index 4. So it's 5 and it's 12. And since it does not have neighbors, we will add the while loop. Okay, so the maximum time needed will be 12. Yeah, correct. Okay, so that's run. And the time complexity will be, since every course will only enter the queue once, will be visited once and in the queue, so it will be n plus the relation length r. Okay, so time space complexity will be, graph is also n plus r.